Students, I'm going to guess part C was the tough one in this problem. Parts A and B are just a matter of recognizing what a catalyst is and what a reaction intermediate is. A catalyst is a substance that is consumed in a reaction and then at a later step reproduced. A reaction intermediate is a substance that is produced and then at a later step consumed. So if we look at the species in the reaction mechanism above, notice that nitrogen monoxide is consumed in step 1. It's a reactant in step 1. And then in step 2 it's reproduced. That makes it a catalyst. So NO is the catalyst. The other species that crosses out in the mechanism is NO2. NO2 is produced in the first step and then consumed in the second step. That makes it a reaction intermediate. In part C of this problem, they give us the activation energies for the uncatalyzed reaction and for the catalyzed reaction. And they say, what's the ratio of the rate constant for catalyzed to that for the uncatalyzed? We're just going to set up a ratio, and we're going to look for things to cross out. We'll use the Arrhenius equation in its original form. The frequency factor A times the number E raised to the negative activation energy over RT. And that's true in both cases. The difference would be that the activation energy for the catalyzed reaction needs to be used for the Arrhenius equation in the numerator, and the uncatalyzed activation energy for the Arrhenius equation in the denominator. The other thing to note is the value of R is given to us in units of joules per moles times degrees Kelvin. It's actually the same universal gas constant as what we had studied with the gas laws, but instead of stating it in liters atmospheres, it's stated in joules per moles times degrees Kelvin. The activation energy has to match at least the energy unit. So they provide us 14 kilojoules for the uncatalyzed reaction. We have to convert that to 14,000 joules, just so the units of R and the units for the activation energy agree. You could convert R into kilojoules if you wanted, but I think it's easier to do it this way. And then for the catalyzed reaction, it's 11,900. Knowing that, let's go ahead and plug in. We'll work this equation a little bit further. Even though we don't know the value of the frequency factor A, it's going to cross out, so you don't actually need to use it. The catalyzed reaction has an activation energy of, we said, negative 11,900 joules. And we're going to plug in 8.3145 for R, and that's units of joules per moles times degrees Kelvin. And actually the unit for the activation energy could be considered joules per mole. And we're going to multiply all of that by, they gave us a temperature up above of 25 degrees Celsius. If we convert that into Kelvin, it's 298. That's a lot of, that's a heck of an exponent to crunch, but we can do this. And if we look for units to cross out, we can cross out moles, joules, degrees Kelvin. Same thing here, moles, joules, degrees Kelvin. It all crosses out. If you pull out your calculator, and the other thing is you can cross out the frequency factor A. It's the same for both the catalyzed and uncatalyzed reaction. So if you pull out your calculator and multiply 11,900 and all over the quantity 8.3145 times 298, we get negative 4.803, and then for the denominator, if I take negative 14,000 all over the quantity 8.3145 times 298, we get negative 5.650 for the exponent. You could just pull out your calculator at this point and crunch those numbers, or you could say, okay, I see that we've got a negative exponent in the denominator, and so mathematically, if I multiply by the reciprocal of the exponent in the denominator, you can bring it up to the numerator, and provided that you have the same base for that exponent, you can just add the two exponents together. In this case, e, the number e, raised to the 8.472 power. And if you punch that into your calculator and round, you get 2.33. That is, the ratio of the rate constants of catalyzed to uncatalyzed is 2.33.